Unit 6.1 begins with 2 parts. So we're going to break this up into 2 parts. So this is going to be 6.1a, and we're going to start off looking at some radical, like parts of radicals, and then some simplifying radicals. So let's look at the warm-up, which is perfect squares. So we know perfect squares are like 1, 4, let's see, 3 times 3 is 9, 4 times 4 is 16. So those are perfect squares. And perfect cubes are going to be just taking it a step further. So with perfect squares, it's 2 of the same number multiplied together to give you that perfect square. With perfect cubes, it's 3 of the same number multiplied together. So like 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And then 4 times 4 times 4 would be 64. Perfect fourths are the same thing, except now you're taking one number, multiplying it together 4 times. So 1 times 1 times 1 is 1. 2 times 2 times 2 is 16. 3 times 3 times 3 is 81. Let's see, what would the next one be? 4 times 4 times 4 would be 256. So that's just what perfect fourths, perfect cubes, perfect squares are. So that's important for when we are doing like a cube root or fourth root. But for parts of a radical, when we're talking about the nth root, which that's what this first section is, it's the nth root, we're pretty much saying, we're rewriting whatever we're saying, like the nth root, we're rewriting it as a to the nth root, and the nth root is just saying that whatever n is, that's our radical. So like say that n were equal to 3, it would be written as a cube root. So it would be written like this. So a cube root, which I can't write a 3 right now, I'm not sure why. Okay. So that's all that really means in basic terms. What we call that number, so in this case, if we have like a cube root, 3 is our index. So whatever that number is, that little number that's on the top of our radical, that is our index. The sign itself, I think we probably all know, is a radical sign or a square root, but we call it a radical. And then whatever is inside of our square root, that's called a radicand. But you'll probably just hear me say whatever is inside the square root. So say that we just have like the square root of 4. There is no number written here. That just means that our index is understood to be n equals 2. Our index is that's just a normal square root. It's understood that our n in that case is equal to 2. So now we're going to look at the actual number of roots that we can have. And just keep in mind that most of the time when we simplify them, we only care about the positive root. That's why most of the time you'll say like the square root of 4 is 2. Typically we don't say plus or minus 2, but for the sake of looking at how many actual roots we have for this first part, I'm going to be saying plus or minus for the ones that actually have plus or minus. So we've got the square root of 16. The answer for that would be plus or minus 4, because negative 4 times negative 4 is equal to 16, and positive 4 times positive 4 is equal to 16. An example of a cube root, the cube root of 8 is 2. Say that we were looking at the cube root of negative 125, that would be negative 5. So with a square root, when we have like a negative 4, our answer is actually imaginary. That would be 2i. But with a cube root, we can have a negative under the radical. That just means our answer is going to be radical, which we're going to do some of that with this box here. And then a fourth root is very similar to a square root. It's going to give you a plus or minus answer. So like The fourth root of 1 would just be plus or minus 1. So let's look at this table. If we have an even index, so that means if we just have a square root sign, or we have a fourth root or a sixth root, and our whatever's under that radical is positive, we're going to have real roots, so we won't have imaginary roots, and we'll actually have two of those, which will be plus and minus. So that's just like saying the square root of 4. And that would be plus or minus 2, or typically we just say 2. Now when we look at an odd index, so that's like a cube root. So if we were looking at a cube root of 8, which that would check the box of having an odd index and a positive radicand or whatever's under the radical. We're going to have a real type of root, and we're only going to have one answer out of that. It would just be 2, and it would be a plus 2. Now, say we had the same thing, except we had a negative 8. So that's going to take us to actually this third box. So we've got an odd index, which is 3. We've got a negative 8. So what's under our radical? Our radicand is negative. We're going to get a real number as our answer, but now our answer would be negative 2. So we're still going to get one root. Now it's just going to be a minus. It's the only difference between when you have an odd index. If it's a positive under the radical, your answer is going to be positive. If it's an odd index and a negative under the radical, you're going to get a negative answer. And then if you have an even index and it's negative under the radical, so say we had just a negative 4, we know that that answer would be 2i. So we're going to have an imaginary root. And then we would actually have 2 answers, which would be plus or minus. But we'll look at, when we're simplifying these, we're really only worried about the positive version. So if a radical has more than one root, the radical sign indicates only that that we just want the positive version of this. So that's why, like I said, when we're looking at like all your life, you've seen square root of 4. We've just written that as 2. We don't write it as plus or minus 2. So that's pretty much what that's saying here. So let's look at number 1. We're just simplifying radicals here, which I'll show you the difference between a square root and a cube root and so on. So if we're looking at the square root of 117, we cannot take the square root of that evenly, but we can break this up into 9 times 13, which will allow us to take the square root of 9, which is 3, and then 13 will just stay in the radical, so that would be our final answer. Now, when you do a cube root, you do it the exact same way, except you're going to break down the inside of your radical into terms of perfect cubes instead of perfect squares. So let's look at 3. We've got 2 times the cube root of 48. So we can't take the cube root of 48, but we can break down the cube root of 48, or we can break down 48 to where we can take out a cube root, which we would break this down into 8 and 6. So you're just going to really need to get familiar with your perfect cubes. So now that we have done that, it will allow us to take out this this cube root of 8, which is just 2. So we'll have 2 times 2 on the outside of our radical, and on the inside of our radical we'll still have the cube root of 6, which that would simplify to 4 times the cube root of 6, and that would be our answer. Now, if we were looking at some different examples, let's see, the cube root of 250. I'm not sure what that is off the top of my head, to be honest. Yeah, I don't think we can take that evenly, but I think, let's see, 250 divided by, let's see, what's 250 divided by 125. Yeah, we could do 125. All right. So now if we're looking at 5, it makes no difference when we have a cube root if what's under this radical is negative, because we can simply rewrite this as the cube root of 125 times, let's say we'll make that negative, and we'll multiply that by 5. So actually we'll multiply that by 2. I don't know what I'm talking about. So all we did there was break down what's inside of our radical in terms of a perfect square that is a factor of negative 250, which that would be negative 125 times 2, and then that will allow us to take out this negative 125, which is going to be negative 5. The cube root of negative 125 is negative 5, and then whatever's left will be left inside of the radical. So that's just another example of doing that. So breaking down the actual cube roots or fourth roots, it's really the same process, except now you need to break it down into perfect cubes and perfect fourths instead of perfect squares. So now we're going to look at radicals with variables. So sometimes, or what we're going to do next and what we're going to get into, will involve a variable with an exponent under a radical. So the process of doing this is pretty simple. If you have, say that you have the square root of x to the fourth, that is simply saying x times x times x times x. It's the square root of all of those. The only way that we can take out a square root is to take out these x's as groups of 2. So another way you could say that is, if I'm taking out groups of 2, that's going to leave me with x times x on the outside of my radical, which is x squared. So the square root of x to the fourth would be x squared. So that's a visual representation of that. Now, another way that people look at this is by saying, okay, what's our index? And they use the index to help you find that, which is another good way, because like the index of just a square root would be 2. That kind of tells you that these need to be taken out in groups of 2. Now the same thing applies for cube roots, except now it's groups of 3, and fourth groups, now it's going to be groups of 4 or multiples of 4. So we'll go over an example to show you what that looks like. So with number 9, we have 32x to the fourth, y to the ninth. So the first thing you need to do is, I would just worry about my coefficients first. So only worry about 32. We can break up 32 into 16 times 2. Then we'll just leave x to the fourth, y to the ninth. That will allow us to take out this exponent, or this square root of 16. So that's going to give us 4 square root of 2, x to the fourth, y to the ninth. Now we need to worry about these variables with exponents here. So we need, since this is a square root, we need these to be taken out in multiples of 2. So for x to the fourth, it's pretty easy. You know that if x is to the fourth power, there's 2 groups of x's that we can take out. So we would end up taking out 4x squared, and we would be left with 2 y to the ninth on the inside. Now the tricky part for some people is y to the ninth, because y to the ninth is odd. You can't take out groups of 2 with 9. You can't take out 2 groups of that. You'll have 1 left over, but that's fine. So another way to look at y to the ninth is y times y times y, y times y times y, y times y times y. So we can take these out in groups of 2. So that's one group of 2, 2 groups of 2, 3 groups of 2, 4 groups of 2. So that's going to be y to the 4th that's taken out. So all that's gone, but this y remains. So the way that we rewrite that is just by leaving. So we would take out, we would have what we've already taken out, 4x squared. We're going to take out 4, or y to the 4th. What would stay in is one of this one y would just stay under the radical. So whatever's left over, whatever's your remainder, just stays inside the radical. So your final answer would be 4x squared y to the 4th times radical 2y, which we'll do one more just to show you what a cube root would look like. So with number 11, we would have the cube root of 216 times m to the 3rd n to the 6th. So first of all, look at your exponent, which a good thing about the 216 is the cube root of 216 is just 6. So then we'll be left with the cube root of m to the 3rd on the inside and n to the 6th. Now, the only thing that changed here was that now our index is 3. That means we can only take out these exponents or variables with exponents in groups of 3 for them to come to the outside of the radical. So if we wanted to look at m to the 3rd, that one's pretty easy. M to the 3rd is saying m times n. So there's 3 of them. That means that one of them, when we bring it outside of the radical, we can bring out one of those. So then we'll be left with n to the 6th. That just is telling us n times n times n times n times n times n. Now, I'll write that out just so you can see it. This is the best way to visually look at it. After you get used to these, they'll become a lot easier. So if we have an index of 3, that means we have to take out, the only way we can take these exponents or variables out of the radical is if we have them in groups of 3. So we've got one group of 3 we have one group of 3 n to the 6th, and we also have another group of 3 that is within n to the 6th. So that means that we can take out n squared. So our final answer would be 6m n squared. And that's the only difference between a cube root and a square root. Is that those, instead of taking them out with a square root, you're taking them out in groups of 2. With a cube root, you're taking them out in groups of 3.